Okay. Now, the eigenvector centrality metric for a vertex is a measure of the degree of the vertex as well as the degree of its neighbors. So we will try to compute that, and then we'll try to interpret the definition based on the results that we get for this example. Okay. Alright, so the method that we use to compute the eigenvector centrality is called the power iteration method. Now we'll go through a sequence of iterations. So in each iteration what we'll do is we'll take up the adjacency matrix and multiply it by a column vector. In the first iteration, this column vector is a unit vector of all ones, and when we do this multiplication we basically get the degree of this of the vertices. Okay, so to get this entry here we multiply row 0 with column 0, and that will get 3. And this row 1 with column 0 will get this, and cell row 1 column 0. Now this cell is row 2 column 0, so multiply row 2 with column 0. Now once we get this product vector, we are going to normalize this. So we are going to use the sum of this square root of the sum of the squares approach that we saw in the first module. So basically what we'll do is we'll square these entries and sum them up and take the square root of the sum. So that is going to be 3 square plus 2 square plus 3 square plus 3 square plus 2 square plus 3 square plus 2 square plus 2 square. So let me show that. So 3 square is going to be 9 plus 4 plus 9 plus 9 plus 4 plus 9 plus 4 plus 4, and then take the square root of it. So that's going to be 7.21. So that's what we call as a normalized value. So square these entries, sum the squares, and then take a square root of the sum of the squares. Then we are going to divide each of these entries by this normalized value 7.21. So 3 divided by 7.21 is 0.416. 2 divided by 7.21 is 0.277. And again 3 divided by 7.21 is 0.416. So these are the normalized values, and they'll be in the range of 0 to 1. Okay. So then now we continue the iterations. So in the second iteration, again we multiply the adjacency matrix with the column vector, and the column vector is the result of the first iteration. Okay, so the normalized column vector. So that's what we have here, and we again do the same multiplication. Row 0 column 0, that will give you this cell. Row 1 column 0 will get you this cell, and so on. Then we normalize, find the normalized value, which is find the square root of the sum of the squares. So square these entries and then take the sum of the squares and then take a square root of that sum, and we'll get 2.59 in this case, and then divide each of these entries by 2.59. We're going to get this normalized column vector or product vector. So continue the iterations. The third iteration, multiply again the adjacency matrix. So that's going to be the same every time with the normalized product vector from the previous iteration. We get this product vector now, and we find the normalized value, take the square root of the sum of the squares, which is 2.67, then divide each of these entries by 2.67, we get this normalized value. Continue the process. This is the end of the fourth iteration. Now when can we stop? Now for exam purposes, I suggest we stop when the normalized value converges to the first decimal. So it was 7.21 and 2.59. Obviously they have not converged to the first decimal. And 2.59 and 2.67 not yet converged, but 2.67 and 2.64. So this 6 is the first decimal I'm referring to. So they have converged. So now we can stop the iterations for exam purposes. Or I may also say just do 3 iterations and you stop after 3 iterations. Or converge up to the first decimal like this, you stop whenever it converges like this. Okay, now there are some tools that will also compute the eigenvector centrality for the vertices for you. They go through until these values converge between 2 successive iterations, the normalized product vector. So what does this normalized product vector indicate? So the entries in this normalized product vector indicate the eigenvector centrality of the vertices. So after you go through 7 iterations, this is the normalized product vector you will be getting. And you see here, so the largest is 0.489 for vertices 0 and 2. So these two vertices are said to have the largest eigenvector centrality. And if you think about it, they have, so it's a measure of the degree of a vertex as well as the degree of its neighbors. So 0 has degree 3 and it has 3 neighbors, and 2 of them have degree also 3 and 1 of them has degree 2. Similarly, 2 has 3 neighbors, 2 of them have degree 3 and the other has 2, and 2 also has degree 3. Now you see 0 and 2 are kind of not at all distinguishable because they have the same degree, they have the same number of neighbors, and 2 of those neighbors have degree 3 and 1 of them has degree 2. So there's no way we can differentiate between 0 and 2, so that's why they end up having the same eigenvector centrality. Then node 3, even though it has degree 3, you will notice that it has a lower eigenvector centrality, which is 0.364. And if you look at the reason, it has 3 neighbors, 2 of them have a larger degree, fine, but 1 of them has a lower degree of 2. So the combination of all these factors make this node 3 to have a relatively lower eigenvector centrality. Now node 4, it has lower degree, so it has a lower eigenvector centrality too. Then node 5 has degree 3, but it has all its 3 neighbors have degree 2. So that's why it has a lower eigenvector centrality. Okay. So the eigenvector centrality kind of comprehensively captures the degree of a vertex as well as the degree of its neighbors and puts together one single metric value. Alright, so let's look at one more example here. So we have a graph of 5 vertices. So you start with the adjacency matrix multiplied by unit vector or column vector of all ones, and again it is like the row entry multiplied by this column vector. So these are the degree of the vertices for the first iteration. We normalize them in the sense that we find the normalized value, which is first we find the squares, 1 square plus 2 square plus 2 square plus 3 square plus 2 square, sum of those squares, then take a square root of that sum of those squares. In this case we get 4.69, then we divide each of these entries by 4.69. This is the normalized product vector. Then for second iteration multiply the adjacency matrix with the normalized product vector, we get this product vector. Now again find the square root of the sum of the squares, we get 2.19. So divide each entry by 2.19, we get this normalized product vector. So continue the iterations like this. So at the end of the fourth iteration, I get the normalized product vector like this, and the normalized value 2.1 converges with the normalized value that you get in the previous iteration. So we can conclude that the normalized product vector at the end of the fourth iteration is your eigenvector. So it's also called the principal eigenvector, and the entries correspond to the eigenvector centrality of the vertices. So 0.616 for vertex 4 is the largest eigenvector centrality. It has a larger degree and its neighbors have kind of normal larger degree. Then node 1, it has just one neighbor and 0.176, and node 2 is 3.352. 3 and 5, 0.484. They're kind of not differentiable from each other because they have same 4 as a neighbor and the other and their neighbors for each other. So 3 and 5 are not at all distinguishable from each other, so they have the same eigenvector centrality. Okay, so I have one more example that you can practice, and again you will converge when the normalized value converges. So we'll go through 5 iterations here, and the normalized product vector at the end of the iteration whose normalized value converges with that of the previous iteration will be your eigenvector centrality. Okay. So again here you can see 0.632 for vertex 4 is the largest eigenvector centrality. Then vertex 3.198 has the lowest eigenvector centrality. You can see the degree of vertex 3 is 1, and vertex 1 has 0.376 as its eigenvector centrality. Okay, so let's stop with this.